Hello there. Today we're going to talk about the Mandelbrot set. What is the Mandelbrot set? This is something that I have been fascinated about for a little bit, for about a week now. And I think it's an incredible example of how an idea that is so simple can generate something that's so complex. In fact, it can generate something that is infinitely complex. First, I want to give credit to Holly Krieger and Ben Sparks of Numberphile for making these videos, which explained the concept to me. They explained it in just a few minutes, the concept of the Mandelbrot set, how to generate it, and they explained it to me so well that I was then able to independently write a program to generate the rendering of it, which you see before you right now. So if you would like to learn more about this, by all means go check out their videos as well. So what you see right here is the Mandelbrot set. It is based on a mathematical formula, which is f of c of x is equal to x squared plus c. Actually, people sometimes see the use of z here instead of x, but I'm gonna use x. That doesn't really matter. This c is referring to this c, which is going to be a number constant. And what you do with this is you choose a c as the constant. So let's say if we choose the number 1 as c. So for case c equal to 1, and then you're gonna do this infinite iteration thing where you plug in 0 for x here. So this would be f of 1 here because we substituted 1 for c here. So f1 of 0 is going to be 0 squared plus c. So 0 squared plus c is 1. That will give us 1. And then after you get the answer for x equals 0, you're going to take the result and substitute it back in to the function. And thus, this is called iteration. We keep taking the output, which is this one, and we're sticking it back into the input and see what output we get next time, and then we keep doing that over and over again. So what is f1 of 1? Well, f1 of 1 is 1 squared plus 1, which is 1 squared is 1, so that's going to end up being 2, and then we take the 2 and stick it back in. We're going to end up 2 squared plus 1, which is 5, and so forth. You can kind of see the trend here, which is that this number is going to get very, very large. So that's one case. Let's try another case. Okay, let's try the case where c is, say, 0. So we're going to end up with f0. And again, we start from 0 as the base case. So f0 of 0 is going to be 0 squared plus 0, which is equals 0. And then you take the output, you stick it back into the input. This is again going to equal 0. We already did that calculation. So this, for the case of c equals 0, this infinite recursion doesn't matter. We always stay at 0. So that's another case. So notice that for the case of c as 1, the series f1 approaches infinity. For the case of c equals 0, the series f0 does not. It does not approach infinity. And it turns out that for some numbers, some values of c, the infinite series approaches infinity, and for other values, it does not. That is the intuition of what this guy is. The points that are colored black in this image are the numbers c for which this infinite series does not approach infinity. So inside here does not approach infinity, whereas out here does approach infinity. Okay, that's what's going on here. However, this is a 2D plane, and if we're only talking about real numbers, then that's only going to be a straight number line here. So there must be something going on here, and it turns out that that's true. So this is a 2D plane because the dots on this image correspond to complex numbers. I hope you remember just a tiny bit about complex number. I'm gonna try to refresh your memory on that. So a complex number has a real part and an imaginary part. The imaginary part is based on I, which means the square root of -1. The square root of -1 is impossible in the world of real numbers, which is why it's imaginary. So an imaginary number might look something like 3 plus 4 times I. So an imaginary number has a real part and it has an imaginary part. So this horizontal axis, that is the real axis, whereas this vertical axis here, this guy is the imaginary axis. This graph is scaled at, over here it's -2 and over here is 2, and in terms of the vertical axis, here we have -2i, whereas here we have 2i, which means the center of this graph is 0 plus 0i, or simply 0. Okay, so give you a couple of other examples. This guy here, this point, right at the intersection of these two curves, that is actually the number 1/4. Although there's no imaginary component because it's directly on this center horizontal line. So there's no imaginary component, which makes it simply 1/4. This dot here is since this is 2i, so this is 0 plus I. This is 1i, this is 2i's, and since this is on the horizontal line, it intersects the 0. This is 0 plus I, or simply I. So which means if this was 1, this is about 1 here on the real number line. This dot over here, that would correspond to 1 plus I. Okay, this, if you are on here or somewhere here, then you have a number that both has a real part and an imaginary part. So what is this guy here? This would be -1 plus I, and this one would be -1 plus -I, and so forth. So what are we saying here? We're saying that if we pick a number, say here, and this number would be 1, and we found this one. We took this number and plugged it into f as its c. We can write that as x squared plus 1. So for this particular number 1, if we keep iterating this function, which as we have already calculated by hand, this function, if we iterate it infinitely, is going to approach infinity. If it approaches infinity, we're going to color it in this light color. But if it doesn't, then we're going to color it this black color. And we've done the calculation for 0, and we can see that it does not approach infinity, and therefore it is colored black. This map accounts for all of the points that we see here, and colors it either black or yellow depending on this rule. So which means if you select a number, say here, that is what would that be? That's probably 1/4 and 1 plus 1/2 I, something like 1/2 I. I'm not exactly sure. I'm just eyeballing it here because this is I. So I believe this is, yeah, this is 1/4 plus 1/2 I. Then if we did this thing to it of x and start plugging 0 here, do the calculation, take its output and stick it back into the input, whatever that is. Take the output, stick it back into it, and we do that infinitely. That will actually not blow up and approach infinity. So that is just simply based on that iteration idea. That's how this graph is generated. And luckily, we don't actually have to iterate over these equations an infinite number of times, because some mathematician has proved that if at any point in time the output of the iteration goes beyond the bounds of this circle, which this circle has a radius of 2 from the center, from 0. If at any point in time you start, let's say you start with this point here, this imaginary number, and I don't know which way it would go. Maybe it goes here, you iterate once, goes on here, you iterate once, goes here, or here. For this case, because it's not supposed to go outside infinity, so it's always going to stay bounded within the circle. But the moment there's a point that goes outside of this circle, we've proven that it will eventually approach infinity once the first time it expands outside of this circle. So that's a rule that we can use in generate this graph to help us save ourselves some computation. Okay, so that's how that works. Let's see how the code is written. I spent a morning writing this code. It took me probably about 3 hours. I want to explain what I did, but first I'm gonna comment it out so I can explain each bit. So first, this is written in TypeScript, and if you don't totally grok TypeScript, that's okay. I'll try to hand wave over it a little bit. So here I'm saying the way I'm representing a complex number is just as an array of 2 numbers. So I can make a constant, say my number, and I want to tell TypeScript that it's a complex number. And if I wrote 1, 2 like that, what I mean, this is my representation of complex number. What I mean is this is a 1 plus 2i. Okay, and then in my program, I'm going to use this array of two numbers format to represent this complex number. So that's the first thing. And then I'm going to need to be able to add together complex numbers. So how do we add two complex numbers? Well, that's actually very easy. You just add the real parts. I'm saying the real part of the number is in index 0 and the imaginary part is in index 1. So I just pick out the real parts, add them together, pick out the imaginary parts, add them together, and let those sums be the respective real part and imaginary part of the result. And then how do we multiply? Multiply is slightly harder. So I actually had to relearn how to multiply complex numbers from Khan Academy. Luckily, it wasn't too bad. Basically, you can imagine that the I was simply a variable like x. And you can use the distributive rule and apply it to complex numbers. So if you wanted to multiply this complex number to this complex number, then what you do is use the distributive rule, which says take this one. Basically, you have two parts in each complex number, this one and this one and this one and this one. You just combine each part in each one with each one in the other one. So 1 times 5 gets us that, and then 1 times I gets us that one, and then 4i times 5 gets us this one, and then 4i times I gets us this one. And then you just do this calculation, this addition, and then you'll get the answer. Now, one thing you'll get at the end is you'll see that there's an I squared, because this guy multiplied by this guy, both of them having an I, you end up with an I squared. And because what is I? Well, remember I is -1, the square root of -1. If we square that guy, if we get square the square root of anything, you get back the thing on the inside. So whenever you see the square of I, you get -1. And that's pretty cool, which just means you can get rid of this term and you flip the sign of this guy, and then you can actually combine with the other real part of this. So you get at the end that. And that is how you do multiplication in imaginary numbers. So basically I encoded that equation into my code. So we get product 1, product 2, product 3, product 4. Those corresponds to these guys. So this is product 1, 2, 3, 4. And then I said, well, because I'm gonna flip the sign of product 2 and throw away the I, I can just take product 1 and subtract it by the product 4, which is what ends up happening. So product 4 is, I do the multiplication, and then I can just get rid of the I and flip the sign and combine it with product 1, which was over here. And as to product 2 and product 3, I can just add those guys together, and that's my result for multiply. So multiply actually is quite easy as well. I have a helper function called square that just multiplies a complex number by itself. That should be self-explanatory. And then I have a distance function which calculates how far, if you had a point, you want to calculate how far it is from 0 plus 0i, then you use the distance formula to do it. You square both the real part and the complex part, add them together, and then take the square root. That's the distance formula. That's the basics of how to deal with complex numbers, and then this is where the real magic happens. So given any complex number, so that is really the, oops. So given any complex number c here, so this is saying fc. You give me any c here, I want to be able to tell you whether it is true or false. That starting from that point, if I did this infinite iteration thing, it's gonna either approach infinity or it's not going to. So that's what we do here. We start with this. Let's say the C was 1 again. So let's start, that's x. We're gonna start x as 0, thus 0 plus 0i, right? And then we're gonna iterate. This is just a counter to keep track of how many times we have iterated. So we're gonna, each time we go through this while loop, we're gonna do this equation. This equation is basically the f of c x equal x squared plus c as a z here. I mentioned earlier, so some mathematicians use the letter z instead of x. No big deal. So this is, we square the x and then we add it to the c. It's exactly this equation. We just keep doing it until we iterate it more than 1,000 times. If we tried 1,000 times, which is, that's the number I deem that's a lot of times, and we still don't get outside the radius 2 circle, it's like, are we still in the circle? That's what it's checking. This circle, are we still, this is 0, are we still inside the circle somewhere? If we get outside the circle, remember, we know that once it gets outside the radius 2 circle, then it's gone. It's eventually going to reach or approach infinity. But if we're still within the circle within 1,000 tries, we deem that it's probably never gonna reach there, and we're happy returning a true, as in yeah, it is black. It is within the Mandelbrot set, the thing that looks like this. So it looks kind of like this, right? So we're happy if we try 1,000 times and it still stays within this circle, then it is within the Mandelbrot set of numbers. And that's really where the magic happens. And as you can see, this concept is there's so few lines required to code it. It's a really simple concept, but the consequence of it is just amazing. The rest of the code is basically, this is the workhorse, which loops through every single pixel within this canvas. So I mean, at the beginning, I do create a canvas element, and there's some overlay, which is for the zooming functionality. And every time you zoom, it'll try to draw the area that you zoom to with greater precision and greater level of detail. Okay, so every single pixel within this canvas, like this one, this one, this one, it loops through for every pixel. I mean, it's got a coordinate. This is from 0 to 800, I believe, and this is again from 0 to 800. So you have a coordinate that's something like that. So this is x coordinate, this is y coordinate. We're not going to use those coordinates because we're going to convert it to the world, this complex number based world that this Mandelbrot set lives in. So our world starts from -2 to 2, and then in the imaginary number dimension, it's -2i to 2i here. So we convert the coordinate system over to this system, which we also notate differently, because I write something like this number, for example, that's actually 2 plus 2i. So but in the canvas coordinate, this number is actually 800 in the x direction and 0 in the y direction. So I have this function that converts between this canvas coordinate to the complex number. And that function looks like this. Honestly, it took me the longest time debugging this function. I had an error in it. I did it by intuition and I was wrong, and it actually took me a lot of debugging time to get this function corrected. But it does seem to work right now. So I use that screen to world conversion function to convert the ij coordinate to a complex number, which with that complex number I ask, is it in the Mandelbrot set or not? If it is, I'm gonna color that pixel black. If not, I'm gonna color that pixel light yellow, and that's all the code that it takes to generate this. Okay, so that was the code walkthrough. Now let's journey through this set and prepare to be amazed. I mean, when you drag to zoom in like that, it'll take that little square, or it could be a big square, but I did a little square. It'll take that and use that as a new window into the world, and it'll redraw, but with greater detail this time. And you can keep doing this. So I'll do it there. And we got greater detail, and you can see we got a miniature version of the thing we were just looking at, and you can also see there's actually many miniature versions of whatever this thing is. It looks like maybe like a little lopsided snowman or something. But something that's really incredible about the Mandelbrot set is the amount of diversity of patterns it has. If you zoom into the edges of this thing, of this shape, let's do here, we actually get a lot of diversity of patterns. So what is some interest? Let's zoom into here, and now things are starting to look weird. Let's zoom in some more. Wow, I mean, that is a beautiful image. There's this, I mean, I don't know what this looks like, a desert island of some sort, maybe, or a really pretty continent. We can zoom in more, and wow, that is really looking really beautiful. In fact, I'm gonna screenshot that one. This looks like just a really beautiful beach island. It's a completely circular beach island with some satellites around it. But the satellites have their own satellites and so forth. And if you zoom in to the satellites, well, it looks like the original thing again. You zoom in even more, and then it's gonna look like the original thing once again. But this is not the only kind of scenery, the only kind of pattern you will find. In fact, you will find a great variety of patterns within the Mandelbrot set. And I've been collecting pictures of them, and these are some of the ones I have found just by navigating and sort of journeying within this incredible infinite world. There's something wrong, I think, with my user interface that I built, but that's okay. We are all programmers. We know how it is. We are not infallible here. Okay, so I'm gonna try to zoom in to another place, perhaps, and wow, where should I go? Oh, whoa! What the heck is this? I'm at a loss here. I'm gonna just select some section in random and zoom into more detail. This looks like there's an earthquake and there's like lava, like there's cracks in the earth and the lava is about to spill out of the earth. That's what that reminds me of. This looks more like an aerial map of some island, maybe tropical island. Let's zoom in more. And yeah, one thing I don't remember if I mentioned is that you can zoom in to this world indefinitely. Mathematically, this is an image with infinite amount of detail, as in you can zoom in, zoom in, zoom in, zoom in, and there's always more detail. You'll never get to the end of the detail. However, in the JavaScript implementation that I have created, you will actually eventually reach the end of where a double floating point number, precision number, can represent the smallness of the difference of the nearby numbers. So it will eventually get pixelated, unfortunately, and perhaps I will zoom in to a low enough level for you to see that. And there is the pixelation. The pixelation starts, and I'm a little bit disappointed. I think there's a way to write the program to avoid this problem. But for now, if you zoom in sufficiently deeply, eventually you'll get pixelation. But regardless, I was still able to explore the different parts of this Mandelbrot set and find all of these fascinating pictures. And it's just an incredible experience. That what you can find within the Mandelbrot set. If you're interested in this, I do plan on making this source code available, all 130 lines of this source code. Having said that, I think there's definitely value to coding this on your own, because you would be so much more amazed. Oh, one more thing. Go on YouTube and Google for the Mandelbrot set. You will be able to find some of these zooming videos, which I highly recommend taking a look at. So this is one of my favorites. It was created by the YouTube user Maths Town, and this he has a he has a very interesting and beautiful rendering of this in sapphire style.